Hello everybody, I'm Eitan Altman from INRIA. I will talk about vaccination games with multipopulations. We are facing a pandemic that already killed 4.5 million people. Computer science, network engineering, math, stat, OR and physics can help in designing simulators, in designing decision-making platforms, collecting and analyzing data, estimating parameters, predict behavior, and detection of changes. We have been applying game theory to epidemiology, so both to electronic viruses as well as to real ones. Here is a worm, the blaster worm, showing a message left for Microsoft CEO Bill Gates by the worm programmer. What is a computer virus? A computer virus is a computer program that, when executed, replicates itself by modifying other computer programs and inserting its own code. If this replication succeeds, the affected areas are then said to be infected. Now, computer viruses require a host program. The virus writes its own code into it. When the program runs, the written virus program is executed first, causing infection and damage. A computer worm, in contrast, does not need the host program. I present this short introduction to convince that epidemiology is relevant not only in biology, but also in computer engineering and software engineering. A Trojan horse is a software used for malicious purposes. It pretends to do a certain thing, but in reality it does something else, such as allow a stranger to read and change the computer's information. Spyware programs are examples of programs that work as Trojans. Trojans are generally spread by some form of trickery. For example, getting users to click on a bad pop-up. Cyber warfare is the use of digital attacks to attack a nation, causing comparable harm to actual warfare and/or disrupting the vital computer systems. I now present our simplest model for virus propagation in a network. It is called the SIS Model because there are two states in which each one of the nodes can be. S is susceptible or healthy, and I is infected. Contaminated nodes become healthy again with rate delta. The rate at which a node becomes contaminated is a constant beta times the number of contaminated neighbors it has. I now introduce the nympha approximation. Let capital VI be the event that the ith node is contaminated. Then the expectation of VI is, which we denote by small vit, is the probability that node I is contaminated. And it is proportional to VIT. The infection rate is proportional to the probability that the node I in this case, is not contaminated, times the sum of indicators Aij, that is 1 for j being a neighbor of I, times the probability that that node j is infected. So this is the nympha approximation. So why is this only an approximation? Well, we use here the product of the expectation of capital VI and of capital VJ. And in fact, they are not independent. But by writing them as a product, we implicitly assume that they're independent. Define tau as beta over delta. From now on, we shall assume that the matrix A, the incident matrix, has 1 in everywhere. This means that all nodes are neighbors of all nodes. Tau is said to be the virality constant. Now, the function that is 0 in all times turns out to be a solution of this ODE for any value of tau. Now, for tau greater than 1 over n, there is a second solution that corresponds to a metastable regime. So this is a regime that is almost stationary, and during a long time it behaves like being stationary. And in this regime, the probability of being infected of a node is 1 minus 1 over tau n. And V is seen to be increasing in n. In this paper, we allow for both competition between consumers as well as between producers. There is a competition between consumers over the suppliers of vaccines. And each supplier may fix its costs, as we shall see. The cost may also impact the demand for each type of vaccine. So we assume several types of vaccines. We do not assume in this paper strategic suppliers. We'll focus on the consumers here. We next describe the state of the system. There is a risk state of a player that corresponds to a subpopulation whose members have a given sensitivity to becoming infected. Examples are age, risk group, or risk groups corresponding to other diseases. In engineering, it could correspond to how sensitive a node is to the virus. The state in this game is given by the combination of local component, which stands for the risk state of the player, and a global component n. N is a matrix of dimension capital M plus 1 times k. NMK is the number of players of type K that choose vaccine of producer M, where M goes from 1 to capital M. NM plus 1, capital M of course, is the number of consumers who do not vaccinate at all. Thus, NM plus 1 plus what we define NV equals N. The cost and the action. The cost of type M vaccine is given as a function that we call C, whose arguments are M, which is the vaccine type, K, which is the risk state, and N of M is the number of users who chose that M. The cost is to be understood in a wide sense. It's not just the monetary cost, but includes also the risk of complications, which is why the cost depends on the consumer type K, or on his risk state. The action of a player is whether or not to purchase a vaccine, and if yes, of what type. The information that is available to a player is How many of each risk type choose to buy a vaccine? The cost of type M vaccine is assumed to be an increasing function of the total number NM of individuals that purchase type M vaccine. Now that we gave the model, we presented the model, we shall focus on the main results. Milch introduced crowding games in paralinx topology. And it turns out that his framework is equivalent to ours. The cost for player I is allowed to depend on the total number of players who make the same choice of I, and also it is allowed to depend on the player's subpopulation. So this is the risk factor of the given player. So in these players, he shows that there exists pure equilibrium in that model. So the conclusion is that pure equilibrium in the multipopulation game exists for the vaccine game. Other result is that in the case that only one available vaccine in the market, then the game is equivalent to a potential game. This is the type of game introduced by Rosenthal. And there's a way to compute it using a finite algorithm that is called FIP, Finite Improvement Procedure. Thank you. I will now explain in some more details these potential games which we obtained and what is the relation between our original problem and these games. So consider a single game population of N players and M companies that produce vaccines. The cost for purchasing from company M is a function C of NM of the number N of M who buy type M vaccines. So we still have several different types of vaccines, and we can allow for competition between vaccine providers, and yet we don't allow here for different types of risks types. The potential is additive. It is the sum of potentials over each one of the M routes, where a route corresponds in our case to a vaccination type. The game can be transformed into an optimization problem in the following sense. Any local minimum of the potential turns out to be an equilibrium in our original game. The equilibria are not unique. In fact, if the problem that we have is symmetric, then we'll have a unique symmetric equilibrium. But we also have non-symmetric equilibria, since we know that there are equilibria within pure policies. Thank you for attending this talk, and thanks for your attention.